Okay, so we're going to do that. And then with the second part of class, we're going to probably do one of those kind of like Are You Ready drills. You know, I got another practice exam made up, and we'll go through that. You guys can fill out the sheet. And then tomorrow we'll do some more of that. Okay, so here we are. And I copied these straight off a Word document, so some things don't really match up. But suppose that they want us to find the solution of this system of equations by graphing. Well, first we're going to draw in our super straight axis, right? and then all we do is we graph both functions and we see where they intersect, right? This one's pretty cake because one of the functions is just y equals 2. So that means the line where y always equals 2, right? So if we want to graph a line where y equals just a constant, that's a horizontal line at that constant, right? And so if this is 2 right there, then this is the graph of y equals 2. And pretend it's a straight line. Okay, and so we graphed one function. Now we just got to graph the other one and see where they intersect. All right, this other function is y equals negative 5x plus 5. Well, to graph that, we're going to go up to the y-intercept first. And so 1, 2, 3, 4, 5. There's the y-intercept. The slope is negative 5x. So we're going to travel down 5 and over 1. 1, 2, 3, 4, 5, and over 1. Okay, we draw the straightest line that we can through there, and then we try and estimate what the heck this point is. Okay, so, I don't know. My graph is super sloppy. To me, it looks like we are at about a half and 2. What do you guys think? Yeah, if this is like 0.5 right there, we come up to this point where the graphs intersect, and then we go over to 2.
Yeah, it should be positive because only it's rise or run, correct?
Yeah, so negative 5 over 1.
Yeah.
You want negative 1.
Oh, hey, good catch. Good job, guys. Look at that. That's awesome. That tells me that this is working for you guys. It's not working for me, clearly, but it's working for you guys. Okay, so once again, we go 5 and over 1. Thank you for correcting me. Okay, so now we're crossing in a slightly different place. So I don't know. This point to me looks like, again, I'll say it's 0.5 and 2. And that is my estimate, right? If I'm having you solve a system of equations by graphing and your estimate is close, I'm not going to take points off. That'd be ridiculous. You know, you guys can see I can't even get my own estimates close. So, let's see now. Okay, so there we go. If we want an estimated solution by graphing, that's it. We just graph them both, and we estimate where they cross. Okay? If they don't cross, then there's no solutions. If it's the exact same line, then there's infinite solutions. Okay? So how about this next one? So how about solving systems of equations using substitution or elimination? What do you guys think? What should we solve this with?
I do substitution.
Yeah? Okay. Sounds good. All right. Let's do some substitution. What's up?
For the second equation, there's a 5 as a common factor, the entire thing. Can you pull 5 out of that and still have the other equation be valid?
Yes.
Okay, cool.
Yeah, absolutely. Good catch. Okay. So we are going to solve. How about we solve for y? Right? So remember, the first step of substitution is take one equation and solve for a variable. To do that, we can subtract x from both sides of this top equation, and we get y equals negative x plus 15, or 15 minus x. Okay, so So now we're just going to take this y and we're going to plug it into this equation. And we could reduce this equation a little bit and it would make everything a little bit easier. We're not going to do that right now just so we don't confuse the problem, but that's an excellent catch from John. So we're going to rewrite this second equation, except for with this y replaced with exactly what we solved for y up above. All right, so we're going to have negative 10x plus 5 times this stuff, right? 15 minus x equals negative 30. All right, so now we can distribute the 5 in. So we have negative 10x plus, what's 5 times 15? 75? All right, minus 5x, and that's going to equal negative 30. Okay, so now we're going to combine our like terms. We're going to get negative 15x on this side plus 75 equals negative 30. Okay, so now we have a situation where we have our variables and our constants on the same side. We don't want that. We want to isolate that variable. And so we're going to subtract 75 from both sides, right? This is a plus 75. We want to subtract 75. So negative 75 and negative 75. Okay, these two 75s equal 0. So we have negative 15x, and that is equal to 30 minus 75, which is negative 45? Right?
Yeah.
Oh, no, it's going in the further direction now. Right. So 105, thank you. 105. Awesome. All right. Now, all we have is the 15 attached to the x. We want to get rid of that, and so we're going to divide both sides by negative 15. All right. Then we're going to get x equals 105 over 15. These are both negative, and so they cancel each other out. What's 105 over 15?
7.
7? Awesome. It's even. And that equals 7. Okay. So now that we found a value for x, we do the last step of this, which is to plug it right back into one of those original equations. So x plus y equals 15. If x equals 7, then 7 plus y equals 15. If we subtract 7 from both sides, then we have y equals 15 minus 7, which is 8. So our solution set is 7, 8. That's where these two graphs intersect. Okay, so any questions about that one? Okay. All right, let's move on to some applications. So this one is kind of like a total value application. So suppose the Juneau Bears are playing an American rules football game. In this game, the Bears scored a certain number of 7-point touchdowns and a certain number of 3-point field goals. The total number of times the Bears scored was 5. The total number of points resulting from these scores was 27. How many 3-point and how many 7-point scores did the Bears make? Okay. All right, so first, this is one of those total value problems, right? And so we usually have like a straight equation that deals with like a pure amount of shots or something like that. And then we have another equation that deals with the total number of points scored by those shots. All right, so right here in this sentence, it already says the total number of times the Bears scored was 5, right? The question is asking how many 3- and 7-point scores did they make? So we're going to say let x equal the number of 3-pointers. And then we're going to say let y equal the number of 7-pointers. Okay, so x plus y is equal to the total number of scores, right? Which is 5. So now we need to do, right? And so that's one equation. Now we need to do the equation that deals with points, right? How are we going to set that one up? What do you guys think? We have 3-point scores and 7-point scores.
Just assign 3 as a multiple to the variable.
Got it,
Or just
right? Yeah, right?
value of the variable.
Yeah, so if we made X number of 3-point scores and they're all worth 3 points, then we have 3X total points for those. And it's the same thing with the Y's, right? However many Y's times 7, and that's the total number of points from those type of scores, right? And they gave us this 27 for the total amount of points. Okay, so we solved the last one using substitution, which is my favorite, but for this one, let's do it just a different way, just to show us how we can. Okay, so I'm going to do this one by elimination, and what do I want to do? I'm going to choose X as my variable. I'm going to multiply this top equation by something that's going to give me the additive opposite of 3x, right? It's going to turn this single x into a negative 3x. So what I'm going to do is I'm going to multiply both sides of this equation by a negative 3. And then I'm going to rewrite it down below. Okay, so once I distribute my negative 3, I have negative 3x. That's exactly what we wanted. I have negative 3y. And that equals negative 15. Okay, so now we're going to add our terms vertically, right? 3x minus 3x is equal to 0. And that's exactly what we wanted, right? If you're not eliminating a variable in this process, something's going wrong. All right, so those go away. 7y minus 3y, well, that's equal to 4y. 27 minus 15, I'm going to do this on the calculator. 13? Thanks, Ed. 13. 12. Calculator it is.
That's 12.
All right, 12. Those are those weird like calculations that I just don't do well. I don't know why. It's only like, yeah, it's like when I'm in front of people and I have to do those, I always screw them up. Okay, so now we've reached this stage. We're in a good situation because we only have one variable, except for it's not isolated yet. We want to get y equals some stuff. So to do that, we divide both sides by 4. Right? Now this is going to allow us to cancel the 4's on this side because 4 over 4 is just equal to 1. And then we have y equals 12 over 4, which works out to 3. Okay, so now let's take that 3 and we'll plug it back in one of our original equations. X plus y equaled 5. If y equals 3, then x plus 3 equals 5. If we subtract 3 from both sides, we get x equals 2. So y equals 3, x equals 2. Let's look back up to see what we defined. So our solution set is 2, 3. And so we scored 2 field goals and then 3 regular touchdowns. There we go. I don't know if you guys noticed that I called it American rules football. What's that? Oh, sorry. All right. Okay. So let's try the other kind of version of these problems, right? This is similar to a mixture problem. I mean, it's almost exactly like a mixture problem, except for we're not mixing percentages. We're talking about total value. Total value is in like cost, right? It's one of those per pound problems. So suppose we have this dude named Gary, and he wants to create his own coffee. Gary has 2 current varieties of coffee. Gary has a cheap mix that sells for $6 per pound. Gary also has a high-end mix that sells for $9 per pound. Gary wishes to create 46.85 pounds of his new mid-grade coffee mix, which will sell for $8 per pound. How much of the cheap mix and how much of the high-end mix should Gary combine to get his desired 46.85 pounds of mid-grade coffee? All right, so right off the bat, let's first name our variables and then we'll create a table, okay? And so the question says, how much of the high-end and how much of the low-end coffee should we mix? So we're gonna say let H equal the amount of high end. And we're going to let L equal the amount of low end.
What letter is that in the first one?
H.
Oh, H.
Sorry. Not like that helps. Okay, so now let's make our table. And this is really the crucial point, right? Like, if you're not sure how to make these tables and you don't know like exactly how to set up the problem, things are going to be difficult. So, like learn how to set up these tables properly. Okay, so once again, like always, on the left side, we're going to have, first, we're going to have our equation that deals with pure weight, right? Pure weight or amount of coffee or whatever, right? And then the next one is going to be our modified equation, right? So this is our pure cost, right? All right, modified down here. Okay, and then across the top, we write the 3 varieties of whatever it is we're computing. Today it's coffee. It might be, in other problems, it might be different acid mixtures or things like that. But today it's coffee, so we're going to write them across the top. So we're going to write high end here on the first column, low end on the second, and then our desired mid here in the last.
Desired as a blend.
Yeah, and so what he wants to do is he wants to take his high and low blend of coffee and make something in the middle, right? And so that's kind of like what we want here. He wants 46.85 pounds because that's how I worked it out to where the numbers were nice. Not for any specific reason. Okay, so let's go about filling this guy out. So this top column, this is usually a pretty easy one, right? The weight of the high-end stuff, well, we just defined that. We defined it as H. The weight of the low-end stuff, we just defined that too, as L. The weight of the mid-grade, well, they gave us that in the problem, right? So, in the end, we're going to have 46.85 pounds of mid-grade. 46.85. Okay, so now let's move on to our modified column, right? And so, if we have H pounds of high-end, and the high-end sells for $9 per pound, what's going to be the cost of the high-end?
Variable, right?
Yeah, exactly. It's going to be $9 times H, right? 9 times H pounds of the high end is how much money the high end is worth. We do the same thing with the low end. Let me look back up at my problem. So the low end was $6 per pound. And so here we write 6L. Okay? And so what they wanted in the end, what they wanted for their mid-grade was $8 per pound. And so over here in the total, in the pure cost of the mid-grade, we write 8 times 46.85. Okay, so now we did sort of the hard part with the setup, and now we really just, these equations just move directly across the rows, right? So H plus L is equal to 46.85. And 9H plus 6L is equal to that, which I'm just going to calculate real quick, which is 374.80.
So the cost for this whole batch.
Exactly, yep. Yeah, and so notice, right, each of these entries in this top equation, these have to do with weight, right? The weight of high end, the weight of low end, the weight of the final product. Each of these entries in the second equation have to do with cost. The cost of the high end, the cost of the low end, and the cost of the mid-grade. All right, so we've got these two equations here. It's looking like we're going to have to do a lot of multiplication. What? Get this thing out of here. It's looking like we're going to have to do a lot of multiplication if we want to do the elimination method. So I'm going to recommend the substitution method. All right, so let's go ahead and do that. I noticed down here that There's only a 6 in front of the L and a 9 in front of the H, so to avoid huge numbers, I'm going to solve for L up here in the upper equation. So, solve for L, right? We do that by subtracting H from both sides. So, L equals 46.85 minus H. Now, we just rewrite this second equation with the L replaced by this stuff. Right, so going to rewrite this guy, and we'll get 9H plus 6 times the L that we found up here, which is 46.85 minus H. And that's going to equal 374.8. All right, so now we just plugged into our second equation. We only have one variable, and so we know we're in a good situation that we can solve. So how do we do this? Well, we're just going to go about the same way we always do, which is get rid of the parentheses, combine like terms, and then isolate the H. Okay, so we have 9H, that stays the same. We have 6 times 46.85. What's that, Ed?
21.65.
For what? For this one? Are you sure?
I got I thought we should, yeah, I thought what you got.
All right. Check your calculator, Ed. All right. Okay. So we went ahead and distributed that 6.
Sorry, I was looking at that.
Oh. So we went ahead and distributed that 6 into our parentheses. What we're going to do in our next step is collect our like terms. So 9H minus 6H, that gives us 3H, and we still have the 281 to deal with. All right, so now we got to isolate our H, right? And so we're going to subtract 281 from each side, right? Minus 281 and then minus 281. Okay, these guys go to 0. And we'll have 3H, which is equal to 374.8. What is it? 93.7. Okay. Maybe these numbers don't work out nicely. All right. So now we have the H attached to the 3 by multiplication, so now's the time to divide. And there we go. H is equal to that number, which looks right. So I clearly didn't. Maybe for this one I just made up numbers. But yeah, that's an ugly number. So I see. Yeah. All right. So this is roughly equal to. We're going to say roughly because I think it just repeats though. 31.23 repeating. Okay, and so we are going to save that in our calculator for our next calculation, right? So H plus L equals 46.85. Okay, if H is equal to this guy, right? H plus L is equal to 46. What was it? 46.85. Right, and then L is equal to 46.85 minus H, and we'll just use our found H to calculate that. So let's see. All right, which is equal to roughly 15.616 with some other stuff.
It's roughly 2-1 ratio.
Yeah. Interesting. All right. So that was it. We had some ugly numbers on that one. Just real quick, do you guys know how to store stuff in your calculator? Store variables? Let me show you real quick. This can be helpful, especially in later on classes. Okay, I use this so often, it's crazy. Okay, where's my camera? Okay, so suppose you have some big number like this, 15.611, blah, blah, blah. To store this and save it for later, right, first we zoom out. See this little store button down here? It says STO, right? Hit store, right, and it says answer into something. Hit this alpha key, and that'll give you access to the green little letters that are above your key, right? And then see right here, I have alpha, there's like a green A here. I'll just store it to alpha A. And then you hit enter, and then it's stored, right? And so now to recall that, you know, if I want to say 2 plus that number, I can say 2 plus, and then I hit the green button to access the green variable again to alpha A. Yeah, and you can save variables for any of these numbers, right? And this really helps for checking your work on ugly problems, which is something that you'll run into next semester more than you'll run into this semester. All right? So that's just a little tidbit there. Okay. All right, so let's move on. So we just dealt with that word problem. Now let's do some easy stuff. So remember, what's the rule on these guys? When we're multiplying two radicals, what do? We just put them both in the same radical, right? It's just this little rule here, right? Root A times root B is equal to root AB. And, and once you memorize this, or even write it on your note card, this really simple rule, like, you get 10 points for these kind of problems on the test. So, if you want easy points, you should at least know these, right? You should know them all, honestly.
What is the final going to be?
I haven't decided yet. I don't think any more than the other exams, really. I'm going to see if I can put it all into one. If I can't, it might be 15 questions or so. It might be a little more, but yeah, but nothing like 50 questions or anything crazy like that. I'll pick out the most important ones. Yeah, it'll be the final.
The whole semester?
Yep, whole semester. And we have 2 full days to review for that. So like I said, I'll make the outline for my test, and I'll make one of these again. And so you guys, it's not like it's going to be a big mystery what's going to be on the exam. Like, later on in later math classes, like, they wanted to make it more of a mystery because, you're supposed to have a more of a breadth. But in here, I'm like, no, there's some important things you need to know for your next math class, and that's what we're going to be tested on in the final. Yeah. Sorry, Colleen. No, just kidding. Okay, so back to this stuff. So for this guy, 40 times 3, right? We put it all under the same radical, 40 times 3. And this is equal to the root of 120. Right? Now, like always with radicals, we can't stop here. We have to see if we can simplify this guy at all, right? So what does this break down into that we can simplify? What do you guys think? 2 times. How about, well, let's see now. Let's start slowly. What is 120 divided by 4? Bam, 30, right? So let's go ahead and start slowly and just kind of simplify it, as far as we can as we go, right? And so right away we can say this is 4 times 30. 4 is a perfect square, which means we can pull it out of this square root, right? And so we break this up again. We use our rule in reverse, right? We have the square root of 4 times the square root of 30 here. But on our next step, we know the value of the square root of 4, so now we have 2 roots 30. So now we have to take a look at 30 and see if there are any perfect squares contained in there. Let's go ahead and just break it down into its prime factors and see. So 30 is equal to 15 times 2, right? Okay, 15 is equal to 5 times 3. The 2 just drops down. We have no perfect squares in there. So that's as far as it's going to be reduced. This is your answer. Okay?
That's it.
Yep. That's it, right? Piece of cake, right? You do that on the test, you get 10 points. That's way easier than those application problems. So, you know, make sure you learn this easy stuff because this is easy points.
Remember that. Stop.
Yeah. Well, yeah, I mean, you stop when you can't go any further, right? It's like when you got something under your radical here that you're not sure about, break it out into one of these factor trees and see if you can break it down into any perfect squares. Yeah. Okay. How about this one? So, the rule for this one is very similar to the rule for the last one, right? Root A over root B is equal to the root of A over B. Right? You can use this rule either way too. You can, you can use it in reverse or forward, this rule. Okay, so for this example, I'm just going to throw 30 over 12 under the whole square root. We'll see what we could do with it. So, what is this? Let's see now. 12 doesn't go into 30, right?
Get 2.5.
2.5? Is that what it,
Yeah.
2.5. Let's reduce the fractions and see if we can take a root of either of them. What are you giggling at over there, Ed?
2.5.
So we got, oh, there we go. What about this one? 10 over 4?
Yeah.
All right. We could actually reduce that a little further, which we're just going to do because that's easier. Yeah, because that's simpler, you know. I mean, you could skip some steps if you didn't reduce it, but we're going to reduce it. So now we have 5 over 2, right? Now we're going to split this guy up. So now we have root 5 over root 2. But we have something bad that we don't like, right? It's not fully simplified if we have a root in the denominator. So we have to rationalize this. Okay, we rationalize by multiplying top and bottom by whatever the radical is in the denominator. So root 2 and root 2, right? And this gives us root 10 over 2. Alrighty. Okay, so how about some other ones here? What about this guy? This guy's kind of ugly. What about the square root of 300? How about you guys take a little bit of time and try and figure out if we can simplify that at all? All right, so what does 300 break into, right? And the first step of this is to just kind of like try and consider your factors, right? What are the factors of 300?
3 times 100.
Very good. Right off the bat, 3 times 100, right? And we know that's going to work because 100 is a perfect square. And so what we want to do right off the bat is kind of analyze these and look to see if we can break them down into 2 factors, at least one of them that's a perfect square. If you can't do that, then keep breaking them down and see if you can find a perfect square in there somewhere. Does what? 2 and 150? Well, neither of those is a perfect square, right? And so,
We're looking for a perfect square.
yeah. And so if you did, let's see now. And so if you said, well, let's split this up into 2 and 150, right? Then you'd want to keep going. And you'd want to say, well, this is maybe 50 times 3, right? And you would eventually find some perfect square in there, right? 2 and 25.
Actually,
And what you'll see here is that we have these factors and this factor that are perfect squares, right? And so, if we wanted to do this, here, I'll just do this both ways, actually. So if we were doing it the easy way and we saw this combination right off the bat, we would say 100 times 3, right? And the square root of 100 is 10, and so we'd have 10 roots 3. If we did it this other way and we said, okay, let's break it down into its prime factors and see what works, we would say the root of 300 is equal to 2 times 2 times 25, which is 5 times 5 times 3. Here, let me fix my 5. Okay, and so then we could rewrite this in terms of squares, right? So we have 2 squared times 5 squared times 3. And then it's obvious that this 2 and 5 can be pulled out, right? Because that's the way square roots work. Something squared, you take the square root of it, you get the original thing. And so we pull that 2 and 5 out. And that gives us 2 times 5 roots 3, which is equal to 10 roots 3. All right, and so either way works. As you can see, it's a lot easier just to try and see the perfect square, but that's not always possible, especially in a testing situation. Oh my gosh, I'm gonna freak out. Okay, so all right, so let's go on to the next one. How about this one? So how about identifying numbers, right? And so we're gonna go through these and we want to attach all labels that apply to each number, right? Perfect square, rational, and irrational. So how about this first one, the number 25? Is the number 25 a perfect square?
Yes.
Why? Exactly. It's a perfect square because a whole number, 5 times 5, equals that, right? So I'm going to write PS for perfect square. Now, is it a rational or irrational number?
That's rational.
It's rational, right? Because rational means you can write it as a ratio. You can write 25 as 25 over 1. So it's rational. All right, so how about the square root of 10? Is this a perfect square? No. Is this rational or irrational? Sure? So a square root is only rational if it's a perfect square, right? If there's a perfect square inside the square root. And so the square root of 25 is rational because it's a perfect square. But the square root of 2 is not. This is irrational. Does that make sense? And that's because the square root of 2 cannot be represented in a ratio of whole numbers, right? There is no a over b that equals the square root of 2. It's completely irrational.
So the issue is that because you'll never get a whole number out of the thing, it's not rational.
Yes, that's a good way of saying it. Yeah.
That's it in a nutshell, basically.
Yeah, and that's and that would be like the non-rigorous definition exactly.
If I'm being entirely honest, that's one of the things that completely passed over my head this entire semester.
Did
Yeah.
Nice. All right.
Better late than never.
Can't divide 25 other than 5 times 5. You get 25.
Yeah, there are other multiples of 25, yeah. But the key is that it's a perfect square, right? Like what works as perfect squares? 9, 25, 100, 81 is 9 times 9, right? Those are all perfect squares, of which 10 is not one. And so 10 is irrational. How about 3? Root 3. It's clearly not a perfect square, right? Clearly not. Is it rational or irrational? Irrational.
So if something is perfect square, then by definition, it is rational. Is there ever a case where a perfect square can be irrational?
Nope. Because, by definition, a perfect square is the square of 2 whole numbers. And the set of rational numbers, I'm getting into abstract algebra here, is closed with respect to multiplication, which means that you cannot multiply 2 rational numbers together and get an irrational number.
Okay.
It's not possible. And so that is in an overcomplicated explanation.
No, it makes sense.
Look at it, is it
Wait, sorry, Bridget, go ahead.
I mean, is there also like 5 times 5 or 7 times 7? Those are rational? I'm so lost.
Yes.
Okay.
And so, let's see now. And so the definition of, let's see now. What do I want to say? So basically, like any square root that we can just work out, right? Any square root that we can work out to a number and that there's no more square root, that's a rational number. That means it's a perfect square. If you can't, right, this is irreducible, right?
So then like with the 10, 2 times 5,
Right.
because it's not being able to be multiplied by itself. Like, I don't.
Yeah, and so the 10, right, and so 10, this splits up, like you said, in 2 times 5, right? Neither of these is a perfect square, which means that this radical is going nowhere. That's going to stay there. We can't pull these out. And that means it's irrational. And so another way to think of irrational is like irreducible, you know, in radical terms, right? And so if we had even the square root of 12, right, this splits up into the root of 4 times 3, which is equal to 2 times roots 3. This is still irreducible, though. And so this is still irrational. Even though we pulled 1, 2 out, we couldn't completely simplify it without any radicals, and so it's irrational. Okay? So the number 5, right? There's no integer that when you multiply it by itself, it equals 5. And so this is not a perfect square. Oops. Not perfect square.
It is rational.
It is rational because you can write 5 as 5 over 1. All whole numbers are rational. Okay, so this one down here. Now this is a little bit weird, right? But you'll notice, right? We cannot reduce this root of 2 any further.
But
What?
I'll learn space.
Okay. So we can't reduce the root of 2 any further, right? And so that means that there's no whole number that we can replace this root of 2 by, right? And so we cannot represent this as a ratio of whole numbers. It's impossible because we can't represent root 2 as a whole number. So this is irrational as well. Okay, so that's, as a rule of thumb, it's just, when you see an irreducible radical in an expression, chances are that is irrational, or it is irrational, right? Because if you can't reduce it, that means you can't write it as a whole number or a ratio of whole numbers. Okay, let's move on a little bit. So, how about this guy? What if, oops, I gotta change that. What if they want us to do this? What do? Well, first of all, geez, that might be in its simplest form. It is, right? If we wanted to extend this radical, we would just have the root of 2 over 7, and that's irreducible. So the only thing left to simplify this is to rationalize the denominator. All right, don't forget about that, right? You guys might look at this problem and say, well, there's nothing to do. But no, we got to rationalize that denominator in order to be fully simplified. So to rationalize the denominator, remember, we multiply the top and the bottom of the fraction by only the radical in the denominator. That is the square root of 7. And we have to multiply top and bottom. Okay. Root 7 times root 7, that's just equal to 7. So on the bottom, we have 5 times 7. And on the top, we have 2 times the root of 2 times 7. Okay, so now we have 2 times the root of 14, over 5 times 7, which is 35. Okay, and since we just formulated root 14 with 2 and 7, which are both prime numbers, we know that doesn't reduce any further. I know, we're really eating up the time today, aren't we? I think we'll get through this. But the practice exam that I was going to give you today, I might just give you that for homework again, and we'll do the same thing tomorrow. Did this work okay for you guys? Is this working okay?
It's
give me a chance, real chance for me to go over stuff that,
Good.
questions I had,
Good.
haven't had a chance to ask
Plus, it
before.
gives us a lot of examples to study over.
Good. And what I'll do is on the practice exam, make sure that you double mark problems that, that were just difficult for you. And we can look up some more in the book tomorrow, and just do a few more if we got some extra time, okay? All right. So, let's move on. Suppose we have this problem, and they want us to simplify this guy. Remember, this is a case of grouping your variables. Okay, so we just group our variables into the squared forms, right? And so x to the 11th, that's the same as saying x to the 5th squared times x.
Oh, yeah. That's
You guys see why that is, right? And so that is because, x to the 5th squared, right? When we apply an exponent to another exponent, we multiply. That's equal to x to the 10, and we multiply it by this extra x. We get x to the 11. Okay, y squared, that's already in squared form. That's easy for us, right? So now we take what is inside these squares and we pull them out, right? And so it's just a plain y and an x to the 5th. So y, x to the 5th times root x. And we're good. That's it.
So the column that x to the 5th in brackets is saying the 5 and then the 2 above, that's multiplying the 5 and the 2.
Yes. Yeah, if you work that out, it would be 5 times 2, and you'd have x to the 10th. Right? Another way to look at these, right? We can do it this way, and this way is great. I like to do it that way. I think it makes a lot of sense. The other way you can do it is look at your exponents and say, can I divide that by 2? Because that's really what we're doing. We're pulling that out of a square, right? And you say, well, 11 isn't divisible by 2. But if I divided that by 2, I would have a 1 remainder, right? So 11 divided by 2 is x to the 5th, right? And your 1 remainder just stays in the square root.
So think of dividing the 1 on the outside to the 1.
Kind of, yeah. And so a square root, there's a little 2 out here, really. That's like a matter of notation, right? If we had a cube root, there would be a 3 out here. They just don't write the 2 because it's more convenient. And so what you end up doing is you divide the exponent by the number of root it is. All right, if that confuses you, stick with this one, though. This is definitely kind of the way that you won't miss anything if you view it that way. Okay, so I have a blank page there. All right, so let's do this one real quick. How about we simplify this? 150z to the 101th power. You guys want to work on that one alone for a little bit? All right, take it baby steps, right? We got a constant and we got a variable.
check this. I gotta hit that quick.
So this was, okay. So z 50, yes, and I believe yes. 6 times. Nice, nicely done.
Or do we need to find a square root of 150?
Is there a square root of 150?
2 times 75. 3 times 25.
Okay, so first things first, let's take a look at this 150 and see what it breaks into that we can use. So 150. 2 times 75. 3 times 25. Look at that, right? Yeah, 5 times 5 for 25, which means this is the perfect square we were looking for. And so the factors we'll break 150 up into is 6 times 25. Okay, so let's go ahead and write that. So 25 times 6. And then our z, if you notice z to the 101, well, that's equal to z to the 50th squared times 1 more z as a remainder.
Oh yeah, this is 2 times 50 is 100.
Yeah.
1, so z.
You got it. You got it. And so we'll take our two perfect squares, 25 and z to the 50, and we'll pull them out. And we get 5 times z to the 50, and then we have what's left under the radical, times 6, so times the root of 6z. And that's it. Oh, one more thing that I actually did not mention.
Grab this 6 from.
Oh, where'd I grab the?
From the. Well, from the.
Right, yeah, exactly. Yeah, if you break it all the way down, you got to remember the stuff that didn't equal the perfect square gets recombined.
Use the 6 to add to the z. 6.
Right, and so I had, after I pulled out the perfect squares, I had 6 in z left, and so those are what remained. So just a real quick kind of trick for your testing situations, not really a trick, just kind of like one of these obvious things that sometimes we don't realize, is that if I am asking you to simplify something like this, you can calculate the original in your calculator and then calculate the end result in your calculator, and if they do not match, you've done something very wrong. So you can check to see if your simplification was valid. You know, you still got to memorize the rules so that you know when it's fully simplified. But if you want to check your original problem by your end problem, that's a good way to do it. Okay, so we got a few more minutes here. I think I got a few applications ready because I know that we all have problems with those. So maybe we'll just run through applications for the last few minutes, and then I'll hand out this practice exam as just another homework. Okay. So application problems. So let's do one that deals with angles first. Whoops, I deleted the important part of that problem. You guys can see, two angles are supplementary. One angle, find the measure of each angle. Okay. It's probably the same thing. All right. So,
Basically, as long as you have filter angles and the answer gets correct.
right, exactly. So, okay, so let's start with one of these total value problems instead. So suppose we have, on average, Americans spend 12.5 hours per month watching videos on both Netflix and Hulu. They spend 7.5 more hours watching videos on Netflix than they do on Hulu. How much time do they spend on each? Okay, so first let's define our variables. They want to know how much time we're spending on each of these sites. So we're going to let n equal our Netflix time. Yeah, it is, right?
Actually, yeah.
And then we're going to let h equal our Hulu time. And if you pay for no commercials on Hulu, there's certain shows that they have contracts where they have to show you commercials.
Seriously.
Yeah, it's so annoying. You're just like, I just paid for no. Yeah. Anyway, sorry to detract from the math problem. Okay, so now we have our variables defined. We're going to come up with our first equation, which is basically like our n plus h equation, right? It's our simple one, okay? And so we're talking about the total time they spend each week is 12.5 hours. Sorry, each month. It's like a weekly for me. So n plus h is going to equal 12.5. Right? So time spent Netflix, time spent Hulu equals total time. Now we're going to use this other sentence to inform us on what that other equation is. So they spend 7.5 more hours watching videos on Netflix than they do on Hulu. Okay, so that tells us that the amount of time they spend watching Netflix is equal to 7.5 more hours than watching Hulu. So that is H, you got it, Ed, H plus 7.5, right? Okay. So when I look at these two equations, I say, what do I want to use, substitution or elimination? Well, when we do elimination, the first step is to solve for a variable. That's already done. So we're going to use elimination because that's going to make things easier. Okay, so what I'm going to do is I'm going to rewrite this top equation, except for with this found value of n plugged in there, okay? So what do we have here? So we have h plus 7.5, right? And that's where I plugged this n into this top equation, plus h equals 12.5. Now I combine my h's, and I get 2h plus 7.5, and that's equal to 12.5. Now I'm going to subtract 7.5 from each side. Okay, that gives us a 0 on this side, just like we wanted, and we have 2h is equal to 12.5 minus 7.5, which is 5, yeah. Okay. Divide both sides by 2 so I can isolate that h. And we get h equals 5 halves. So we're going to enter that guy into our top equation and solve for n. So n plus h, which is equal to, 5 halves, and that's equal to 12.5. Okay, we're going to subtract that 5 halves from both sides. And then we get n equals 12.5 minus 2.5, that's equal to 10. All right, so our solution set for this guy is, let's see now, h comes first in the alphabet, so we'll list that one first. It is 5 halves, comma 10.
Solution set.
Yeah. Okay, once again, we use substitution there, so we solved for a variable and plugged it into the other equation. All right, let's do a total value problem. Another one. Actually, let's do a mixture problem. Yeah, since we're running out of time, we haven't done a mixture problem yet today. Let's do one. Mixture problems are super fun. Yeah. Oh, this isn't aromatherapy. This is about acid. So, right. So Jerome's experiment requires him to mix a 50% acid solution with an 80% acid solution to create 200 milliliters of a 68% acid solution. How much 50% acid solution and how much 80% acid solution should he use? Okay, so right off the bat, let's define our variables. Okay, so let's go ahead and let x equal amount of 50% solution. And then we're going to let y equal the amount of 80% solution. Next step, as always, we build our handy dandy table. Okay, and just like always, we're going to write our two equation types on the left side here. the first equation is going to be total volume. The next equation is going to be pure acid. All right, and I'm just going to write as a reminder that this is the modified. All right, and that's just for my own, just so I realize that these always have a straight equation, they always have a modified equation. Okay, and across the top, we're going to write our different solutions we're dealing with. So we have our 50%, we have our 80%, and we have our final, which we wanted a 68%. Okay, our total volumes, right? We just labeled these. Volume of 50% is X, volume of 80% is Y, and the volume of the 68 is what they gave us in the problem, which is 200 milliliters. All right, now for our modified, right? How much pure acid is in X milliliters of 50% solution? What do I put right here? You got it, exactly, 0.5x, bam. That is 50% of however many gallons or milliliters X is. So we do the same thing with the Y, right? How much pure acid is in 80% of Y milliliters? Well, that is 0.8 Y, exactly, right? How much pure acid is in 200 milliliters of 68% acid solution? Well, 0.68 times 200. Don't forget this step. Remember that this guy's got to be modified, right? It's really tempting to just write the 200 in there, but that's not correct because we're dealing with pure acid. All right, so down below, write out our equations. X plus Y equals 200, and we just read across this bottom row to get our other equation, which is 0.5x plus 0.8y, and that is equal to 200 times 0.68. Nice, 136, 136. Okay, all right. What do you guys think? Substitution or elimination?
I kind of want to see elimination.
Yeah, I do too. Okay, so we'll try elimination on this one, okay? So, for elimination, we're going to choose variable and we're going to try and create an additive opposite to that variable. I can see here that x, if you multiply one by two, you get the other, right? So I'm going to choose that as my target. What I'm going to do is I'm going to turn this 0.5x into the additive opposite of plain old 1x. Okay, and so what do I multiply 0.5x by in order to get the additive opposite of x? Negative, you're thinking in reverse, right? Not negative point something. Negative 2. Right? Were you guys thinking of the other equation?
So
Right.
you're simply adding those two together, correct?
Yes.
So then you need negative 0.5 to have the same value.
But I'm multiplying by the bottom equation though, right? And so if I multiply 0.5x by a negative 2, then I have a negative 1x. Hold on. All right, let me rewrite this. Let me go ahead and write it all out, right? And so when I distribute the negative 2 in here, right?
You're taking
I
a
get-
different approach.
Yeah,
I thought you were applying the multiplication to the higher equation rather than the lower equation.
that's what I figured you guys were
Okay, no, I
thinking.
was
Yeah,
wrong.
yeah. And so you could do either. Honestly, you could totally multiply this upper one by a 0.5. I just usually like to do my multiplications by whole numbers, even though with this one it would be just as simple, honestly. So we're going to multiply this 0.2 in, right? That gives us a negative x, and we'll have a minus 1.6y, and that's going to equal a a negative 272. Right? So, take this upper equation, and I'm going to write it below. X plus y equals 200. And then we're going to go ahead and sum vertically. So, just like we wanted, we have additive opposites on the x's, so those are going to go to 0. Right? Y minus 1.6y is equal to negative 0.6y. 200 minus 272 is equal to negative 72. Okay, so now we're going to go ahead and divide both sides by a negative 0.6. All right, these negatives will cancel, and we'll do the rest on our calculator. You got what? Nice. Me too. All right, so we have y equals 120. So now we're just going to plug it in our first equation. X plus y must equal 200. If y equals 120, then x plus 120 must equal 200. And then we're going to subtract the 120 from both sides. And we get x equals 80. So the solution set to this problem is 80, 120. Okay. You know, and yeah, just so you guys know, like, yeah, we completely could have multiplied this top equation by a negative 0.5 and it would have worked out just fine. Okay. Yeah, we got 8 minutes left. I'm not going to drag you guys through another one. Thank you for hanging out and sticking with me today. Oh, let me hand out your homework assignments too. Never forget